let me say that what I'm going to talk about is really a kind of a red herring. It's totally different from what is done here, but it has one important aspect which connects to what I certainly was always admiring with Ludwig, is namely that good mathematical results in general have also a quantum version. And this is something which is even true in fields which are totally different from what we have heard here, namely in fundamental theorems of probability. And this is something which I want to talk about. In particular about something which I want to motivate with the following example from Dadaismus. I want to show you how your computer works when you compress some data with transforming a document into something which is of the form .zip. This is in fact something in Swiss German, and it means is he allowed to do that? I'm surprised that he is allowed to do that. So I use this sentence because it shows in a simple way how the Lempel-Ziff algorithm works. The Lempel-Ziff algorithm is something which encodes an array of letters in a lossless way, in an optimal way. So the first thing is that I will show you how the codebook, so-called codebook, is produced. You read from the left to the right, and we start from the left and say, D, I don't know. Therefore, I put it in the codebook. A, I don't know. Therefore, I put it in the codebook too. Now comes the next. A, I already know, but the word AD, I do not know. So I put AD in the codebook. So A already know, AD I already know, but I don't know the word ADA. So, and so forth. And know the letter D. I don't know the word DA, so I put DA in the codebook. I know the word DA, but I do not know the word DAA. So I know DA, so I now go progress. So I don't know the word A. So now this is the first entry in the codebook. This is the second one, the third.
No, the last one. The last one.
Yes, that's true, but it is because it stops here. You know, I have to, okay. Yeah, I mean, I should, of course, continue, but it stops here. Okay. I don't have to put that in the codebook, you are right. So this is the fourth entry, the fifth, the sixth, the seventh, the eighth. So now I tell you what I'm going to send to my friend. Alice to Bob is usually now the thing to say. Now the code I'm going to transmit is D, A. Now here I don't transmit AD. I say, you know, if I take D off, A has already been here. So it is 2 D, referring to the pointer. I point to E, to the second entry, and I add D. Here, to transmit this word here, I know if I take off A, I already have AD, namely at the third position. So I write 3A. Next, I have a new word, which is DA. No, that's not true. I'm sorry. D is already here. This is 1A. Then I have here DAA. So DA has already appeared before. To the left here, it's 5. 5A. DA is 5D. Now AA. And okay, and DA. So this would be the code which is transmitted. And this system, for long sequences, is optimal. So this has to be shown, but I don't want to do that. Now, what I want to point out at this now is the only important aspect of this, namely that it is basically one-dimensional. It's linear. You have to go one after the other. If you want to transmit something like an image, which is intrinsically two-dimensional, or even some higher dimensional data, then this system of encoding is not good. Lempel and Ziff have proposed to use a piano curve to fill a two-dimensional image. This is fine, it works, but it doesn't take into consideration the two-dimensionality of neighboring. So the correlation between neighboring points in two dimensions is not reflected in this code. So, and this is what we were trying to find a generalization which is multidimensional for a multidimensional Lempel-Ziff code. So much for the motivation. We have been working on that since quite some time, in fact, several years. Now, let me first tell you, explain you some words which come up in the title. Multidimensional universally typical sets and the Lempel-Ziff algorithm. Lempel-Ziff I explained now. Multidimensional is clear. And now universal lossless encoding algorithms. Lossless is simple to explain. Namely, you want to transmit signals from A to B in a way that you can reconstruct the signal without mistake. This is something which is important in many cases. In many cases, it's silly to do. For instance, if you transmit images, it's silly to do because you can transmit images in a way which cheats the eye in a way that you don't even notice it, and the loss you have in the data is quite amazingly high. Now, what the first line, data modeled by stationary ergodic random processes. The idea is that the data which you want to transmit should be taken, considered as typical configurations of a random process. And if this is an idea which was introduced already by Shannon in the very early days, and is a very, very successful ansatz to do it in this way. That's what I just said. Now, universal. What does universal mean? It means that about this ergodic process or about this stationary process, you don't want to say more than something on the entropy. The entropy is everything you know, and except that, you don't want to say anything. In fact, not even about the specific value of the entropy. No, you want to make only an assumption on the that the entropy is not larger than a given number. So this is what is meant by universal. We want to construct typical configurations and processes from a whole family of processes, and the family is just characterized by an upper bound on the entropy. So the strategy will be to construct universally typical sets for all random processes which are bounded by a given number. Now, let me be more specific. We look at a spin chain first. I'm now coming back to one-dimensional, and I will generalize that to several dimensions later on. We have configuration A to the Z. Think of A to be the letters 0 and 1, or something more complicated, but that's good enough. Just take for A the alphabet 0, 1, and we look at all the configurations on the one-dimensional lattice Z. And on these configurations, we assume to have a measure. And now I want to explain the different terminologies. I want to say what is asymptotic equipartition property is the following. You look at the measure of x 1 to n. What's that? I look at first at the configuration x in AZ, which is nothing but a function on Z with values in the numbers 0, 1. I restrict them to 1 to n, and I take the cylinder set. In other words, all configurations which restricted to 1n have this, the given configuration 1n. And the measure of this set is 2 to the minus n entropy of the measure mu. The entropy of the measure mu is, as usual, the von Neumann entropy in the thermodynamic limit. So this is a number which is typically small, and this is something this is a property which is called asymptotic equipartition property, and it says two things. It says that if we have this property, asymptotically, the measure or the probability of this configuration is always the same. So we have an equidistribution like in statistical mechanics, well known. It holds here. Now, the total number of elements in this typical set is supposed to be 2 to the nh of mu. In other words, the product of that, which is the total weight, is 1. So, in other words, this set tau is in a way minimal. So that's what is meant by full measure. And now we know what it means, small entropy typical set tau. That's what is meant by this expression here. From those assumptions here, follows that here, because we have already the full measure, and so this is hardly observed. So now I come to the celebrated Shannon, Mcmillan, Briman theorem. Oh, give me my regards. So we are again considering an ergodic process, and then there is this famous theorem which states that for almost all x in AZ, we have this convergence here. Namely that, Shannon proved this in probability, but it has been improved, and it has by Mcmillan and Briman, and it means pointwise in almost surely. So we have this convergence, that the logarithm of the measure mu of x of n converges to h of to the entropy if we normalize it with 1 over n. Are you still with me? Now this has been generalized to higher dimensions in particular, and even more to amenable groups. But what we are, what I'm focusing on is this ZD. It's a non-trivial generalization by Kiefer, Ornstein, and Weiss. So I mention it. It's not just simple. So now I must introduce some notation. I'm sorry for that, but it's unavoidable. So what I have here is a d-dimensional cube, discrete, with length n, the side length n. Let me make a plot here for later purposes. So this is 1, 2, 3, 4, 5, 6, 7, 8. So we have lambda 8, and for d equal to. So now we are looking into a lambda n, with other words, to configurations on this discrete lattice, which associates to each of point a 0 or 1. So now let me formulate the theorem and then comment on it. For a given number h0, which must be positive, we can find a sequence of typical sets tau n of h0 contained in sigma n. I recall you, sigma n was the set of configurations on the lattice lambda n. So that for all measures mu which are ergodic, such that the entropy is below H0, we have the fact that tau n is asymptotically a full measure, of a full set.
What is mu n?
Okay. Yes. Mu n is the restriction of mu to sigma n, in the sense that mu n of x1 to n is equal to mu of the cylinder set. But forgive me that I usually do not write this bracket here. I identify the configuration x1n with its corresponding cylinder set x1n. I could have avoided that. I just could have dropped the n. So here the first line says that the tau n has full measure, and the second line means that asymptotically we have that the number of points in, or the number of elements in the typical set is 2 to the n h0. If I have h0 here. Okay, if I take the typical set as claimed to exist in this theorem, the number of elements grows exponentially, and the factor here is given by this h0 here. And it is an optimal choice. I don't want to go into that at the moment. So let me explain you one word about the proof, because this theorem is constructive. So since it is constructive, it will be used later as a method for encoding. So I want to talk now about the so-called empirical measure, which carries a tremendous number of indices, namely 3, k, n, and x. And let me tell you what those indices mean. N is larger than k, and what you should think of is you have a k box here, and here you have an n box. Okay, we have here an n box, and here we have a small k box. And now we look at the configuration x. What is a configuration x? It means that to each point here we have associated a 0 or a 1. So let me consider x in sigma n, or this here is the same as saying x is an element of a lambda n, with other words a function on lambda n with values in a. Now I make a very simple thing. I look at this x and give myself a configuration on lambda k. So Now I have a configuration given on this small square. And now I look how many times does this X show up, contain this configuration A. So, for instance, I look here, and I look, since I have an X which gives values on the whole set, I look at the configuration given here. Is it equal to A or not? If it is equal to A, I count it. If it's not, I don't count it. So I take the counting measure of all K blocks in this large thing here, and just this defines a measure. It's just okay. So this is meant by the empirical measure. Did I get across that? Okay. Okay. So we just look how many times the configuration A on the K block shows up among the X configuration on the large block. I do that in a non-overlapping way. In other words, I look at this here, at this here, at this here. I do not look at that here. Now, there is a construction of this typical set tau n h0. Namely, we take x in the sigma, which is a configuration on the whole z to the d. We compute the empirical measure and its entropy. If this entropy is below h0, I say yes, this x is good. I take it and I put it into tau n. I told you that I take an x in all of sigma. This pi n means that I restrict it to the box lambda n. So once again, I take an x in which is an element of sigma, in other words, a configuration of all ZD. I compute this empirical measure. I compute the von Neumann entropy divided by 1 over KD. And if it's smaller than H0, it's fine. Now I have to tell you something about how to choose k and n. I cannot choose k equal to n. This would never work. So what I have to do is I have to choose k exponentially small in n. This is what this next statement means. So I have to choose k in such a way if I wanted everything to work fine. So
it still must have some content, so it cannot be 1.
Yes, of course. It's also a bound from below. Yeah. So then I have also I get this inequality as a result. So now another remark about the proof, and also something which is important for the algorithm is the following. My empirical measure can be used to compute the entropy of this measure here, which is rather surprising and remarkable. So that this here converges almost surely to the h of mu. Now let me confuse you. You know, I told you that we have a bound on all the entropies, so we can have many different entropies in our scheme. We can have many measures, for instance, h of mu1, h of mu2, yeah, so. Now, this limit here doesn't really know anything about the measure. So, in other words, this limit here, which doesn't know anything about the measure, converges to many different values, h mu1, h mu2, h mu3. Yeah, so, now, what is the solution of the paradox? It means that we have measures which are mutually singular, live on different sets. So they are characterized by this x. And so it can very well happen that, that the convergence is convergence towards different values of the entropy. So in other words, in this sentence here, mu almost surely, there is a lot buried, namely the zero sets are all the time, they are very much dependent on the measure under consideration, which is labeled in the x here. So that's the reason why this limit here can have different limit points depending on whether x lives in the subset which belongs to to the support of one measure or the other measure. Yeah. Now, the main reference for what I was telling you is this wonderful book by Shields on the ergodic theory of discrete samples, and an article which we published. And I will now at the end come to how is this used in generalizing Lempel-Ziff algorithm. What you do in order to generalize the Lempel-Ziff algorithm to higher dimensions is the following. You take a configuration X in sigma n. You compute its empirical measure. Then you compute the entropy. From that you compute the corresponding typical set. Now you know that the number of elements in tau n is 2 to the n to the h. The entropy, the normalized entropy of that. You label those elements in Tn, 1, 2, up to 2 to the n. And now, if your configuration you want to encode becomes an element of in Tn, you get you just transmit the label of the element in the typical set. If not, you take you transmit the full signal. but since the full signal is not in Tn is very, very rare, this happens very rare, very seldomly. So one can prove that in this way you have an optimal way of transmitting signals in a multidimensional setting. In fact, we are about to publish a paper where we do some experiments on that, and I have written some algorithms to do that using the standard pictures of the boat and Lena and all those, and we can compare it to the present results, which are used in compressing images, and they compare quite favorably. Mm-hmm. So that's what I had to say, and I thank you for your attention.
How does your result compare for d equal to 1 to the old previous result?
Then you get the same. You get the same. Yes. Mm-hmm. Yeah. Sure. Mm-hmm. Mm-hmm. Yeah. Yeah.
May I ask some general questions? Maybe I would like to ask you about the stability of this procedure. Assume that there is some small noise.
Yes.
Can you estimate? And you want to transmit some information, but assume that there is some diamond who makes some small influence. Mm-hmm. How all this is stable? How you can believe on your result?
You mean noise in the sense of you have as soon as the noise is given by an ergodic process,
yes.
Then it's okay. So it depends on whether your noise is if it's not an ergodic process, you certainly have a problem. So in this case, what an information engineer would do, he first would denoise the signal, where there are totally different algorithms for that. And after having denoised the signal, he would then transmit the signal in a lossless way. Mm-hmm.
But if Eve is doing something evil,
this is a totally different ball game. Here the aim is to have a lossless transmission, and the question of interfering in an evil person is not considered. This is a field interesting in itself, but I didn't address that. Mm-hmm. Yeah. Mm-hmm.
I still didn't understand why you have rejected the combination of space filling curves. Lempel algorithm.
Yeah, because the space filling curves do not respect the vicinity between points. If you have a piano curve, you can have in 2 dimensions 2 points very close to each other. However, on the piano curve they are very far. So,
but the measure of the points which are far is very small.
That's true. We have made experiments on that, and we compared the compression on piano curves with the technology which is used today, which is a technology which is not mathematical in a sense, or partially mathematical for images. It uses a model where the probability of occurrences of the signals is described by a generalized Gaussian measure. And in fact, this method, which I could explain in more detail, is about 30% better than the piano curve, experimentally.
With respect to piano curve, I call it TV system, yeah?
Yeah.
And then it's very important. The very bad theorem about Hilbert spaces is that all infinite-dimensional separable Hilbert spaces are equivalent.
Yes.
But of course we know that L2 of R2 and L2 of R1 are
It's totally different, yes.
So
Although they are in a way the same, yeah. So they're totally different.
So
Yeah.
it's important not only the structure of Hilbert space, but also number of independent observables and so on.
Yeah.
Something like this.
Yeah.
So you mentioned in the beginning that you would say quantum.
Yeah. Okay. This we are about to quantize that. So as we have quantized the Shannon-Mcmillan theorem, the Shannon-Mcmillan theorem has a beautiful extension to quantum mechanics, but it's okay.
But
So, you know.
0 and 1 is fermions, and somehow like Toft ones too.
We have used bosons. We have used bosons, yeah. But no. Yeah.
Okay, so let us continue in 3. Oh, thank you.